Thank you guys for being here. Today I'm gonna start by presenting the title of my review article called An In-Depth Systematic Review and Experimental Insights into UHPC for Structural Repair Applications. So I'm gonna start by an introduction, and then I'm gonna talk about the current repair practice in the industry, then what leads us to the UHPC, then different case studies from the 15 experimental literature review articles. I'm not going to focus on the 15, I'm just going to focus on 5 today, which are the pioneering studies according to my understanding. And then I'm going to talk about the experimental work, limitations, and then we're going to end up by conclusion. So nobody can deny that the situation of our infrastructure is getting worse and worse, whether roads, bridges, and all the major infrastructure are worsening with time. It is after 1940, after Second World War, the revolution in infrastructure, we started having a lot of, major infrastructure projects. In the United States, for example, most of the bridges were built after 1940, 1945, having in mind a service life of 100 years. So it looks like we are nearing the end of life of these structures. So according to the Federal Highway Administration, more than 185,000 bridges are in need for urgent consideration, where more than 46,000 of them are needing the end of their service life. And the retrofitting budget was $123 billion. A lot of opportunities for research lie behind this number. So currently, the practice is to repair our infrastructure using steel plates or fiber reinforced laminates. However, despite being successful for a limited number of time, there are a lot of limitations concerning the shear failures, for example, for the steel plates, and the steel by itself is corrosive. For the fiber reinforced polymer laminates, it's a difference in the behavior of the material, because the carbon fiber and the cement, they don't adapt in terms of, for example, modulus of elasticity and all of that. So we're going to end up having a lot of delaminations and a lot of brittle failures, which we are trying to avoid. So the idea now is to think of a new material which can be cementitious, highly performant, durable, and at the same time being flowable and workable given the tight areas where we're gonna do our repairs. So that's why now we are thinking of an ultra-high performance concrete. So the UHPC is made of cement, SCMs, fine sand, fibers, and high-range water reducers. And the secret behind the formulation of the UHPC is the low water cement ratio. This is a representation of how the regular concrete particles look like and how the UHPC, as you can see for the normal strength concrete, we have a lot of coarse aggregates and we have a lot of voids between them. For a water cement ratio that usually starts at 0.4. For UHPC, it's highly dense matrix, and usually the water cement ratio is between 0.2 to 0.25. So for the mechanical performance, there is an agreement that the compressive strength has to be more than 120 MPa. For the flexural strength is more than 23 MPa, and for the modulus of elasticity of concrete, according to the literature review studies I've reviewed, it's always more than 40 gigapascal. This is a small representation of how the difference in durability between UHPC and normal strength concrete. Sorry, can I please silence my call, please? Yeah. Sorry. So that's the difference between UHPC and normal strength concrete. And these are the two specimens having the same dimensions, being exposed to seawater in an abrasive environment for 10 months. And you can see from the normal strength concrete that there is some scaling there. And, it really looks bad. So these are the case studies. We're going to talk about, as I said, like 5 of them. So this study was done in 2016. The idea here was trying to improve the flexural capacity of repaired concrete specimens. So they tried different configurations of UHPC layer. The first one tried to put the layer as we did in our experimental study at the bottom, the second one from the sides, and the third one is going to be like a U jacket, you know. So we can see that there is a lot of improvement from 7% up to 89% for the three-side jacket. And here the authors, they tried to compare between the sandblasting and the epoxy adhesive bonding. And of course, sandblasting yielded better performance. However, for that three-sided jacket, there is a problem and there is a significant compromise in ductility. Now we are having the behavior of an over-reinforced concrete beam. And if we define the ductility by a ratio, it's the area of steel reinforcement divided by the amount and configuration of UHPC. Just think about it. When you have a three-side jacket, you have more steel fibers. So it means you have this factor at the bottom. This denominator will be more, so the ductility will decrease. And that's why we don't have any deflection hardening behavior into this curve. The other study was in 2017, which is one of the fewest studies that focused on the behavior of the slab. So here there are two rehabilitation schemes. The first consisted of keeping the same thickness of the slab while, damaging that area like we did in our experimental study with different thicknesses, 20, 32%, 50, and like just to compare for UHPC. And for the overlay series, so we're gonna keep the 100 and we're gonna put different layers of UHPC, and we're gonna also try to study the behavior of putting reinforcement inside the UHPC layer. So there is an interesting behavior here, which is, for example, for the specimen RE0, the ultimate cracking load was 61.08. When we add UHPC, it's gonna be less than the normal strength concrete. When we go more, it's gonna decrease more. So there is a problem, right? So the authors have investigated that the UHPC layer that reaches up to the top of the reinforcement exactly, it's gonna prevent the shear transfer between the longitudinal reinforcement and the concrete, which will lead to a weak interface and lower the ultimate load. So the idea behind this study is we can provide reinforcement as long as we respect the minimum cover between the edge of the rebar and the interfacial transition zone. This is another study that tried to investigate the shear capacity. It's a concrete T-beam. They tried the more or less same configuration of having a bottom layer and the side layers and a U jacket. So you can see in some of the studies, they tried to put some shear studs. The idea there is because they started noticing some faders in the behavior and the shear behavior. That's why they tried to put some studs in order to limitate that reduction in shear there. Again, UHPC did a very good job, and we are having like up to 153% for the ultimate shear capacity and up to 84% for the beam for the cracking capacity as mentioned in here. However, like when we put the UHPC layer at the bottom, it's not really practical to have it up to the ends or up to the supports, because let's say that you have a bridge. Under the supports, we're going to have the bearing pads. So that area is very limited. So we cannot really put our UHPC layer. So the authors tried to investigate that behavior as mentioned in here, and they found out that the cracking capacity decreased up to 15%, and we started having a lot of separation faders in that area. So for that reason, they tried to put some shear studs in order to improve the behavior. But even with the shear studs, there is a very low contribution to the shear capacity and beam stiffness. Bearing in mind, we have a better, greater ductility in that situation. Also, a lot of studies try to investigate the lateral strength. I mean, when I say the lateral, basically the seismic behavior. For example, this study, and I think that everybody have have seen these kind of specimens in our concrete lab. So it looks like it's a popular way to investigate the seismic forces. And this study tried to put different rehabilitation schemes. One of them consisted of installing of a mono UHPC wide strip, and the other one consisted of installing multi-narrow strips to check the plastic hinge, specifically how it's gonna form when you have footing and the column on top. So we need to think about the UHPC performance in there. So this is a comparison between the two. The first one, we had some spalling and crushing in the interface between the footing and the column. When we put the WHPC jacket, you can see we don't have any problems in spalling. It's just some minor cracks along the shaft of the column. When we move to the multi-narrow strips, here it's a better behavior, less cracking. So here, like the authors are trying to compare which one we can use when we have a need for flexural strength and which configuration we can use when we need more seismic resilience. So this is the reference configuration. We are exposing our columns for different drifting percentage. And for the WHPC jacket, we have an issue that the author talked about called plastic hinge relocation. So let's say that we wanna repair this specific area here. And let's say that the plastic hinge is around, for example, 1 meter. So I'm gonna put into that area between the footing and concrete, I'm gonna put my WHPC jacket, but you know what? That plastic hinge that caused this kind of damage in here is gonna relocate to the top portion, which is gonna be a problem, right? So here we need to bear in mind this kind of ideas when we design our UHPC to prevent this kind of problems that can happen in the future. For the UHPC, we didn't have this kind of issues, and for this reason, to improve the seismic resiliency, the authors have voted for this kind of repair. Now, talking about torsion, so this study tried to investigate beams in torsion. They tried to fully wrap the beam, U-jacket it, or left and right from the sides, and of course, the full wrapping will yield a better performance, whether for the cracking torque or the ultimate torque. But when I think about it, does it make sense? Is it practical to have a full wrap in the industrial context? Of course not, right? Because it's a monolithic pouring, and the top portion, you don't have any control over it. So now we'll move to our experimental study. So we started first by establishing the mixed design. We did the particle size distribution. We tried to have this kind of wider distribution for our particles. The particle size distribution was optimized using the EMA software and using the modified Anderson model, and the factor Q was equal to 0.21 for this study. So we went to the lab. We casted all the different specimens we have for the modulus of elasticity, for the compressive strength, and for the flexural strength. So these are some pictures from our studies. And talking about the mechanical properties now of UHPC. So as Great mentioned in the beginning, we had almost 117, I would say, MPa compressive strength, which wasn't expected because we were expecting more than 120. But given the size of the silica fume we got, it looks like that's reasonable. For the flexural strength, a very big increase, almost 5 times than normal concrete for the UHPC. And for the elastic modulus, there is also a good increase from 28 to 43.1 gigapascal. Talking about the modes of failure, talking about the picture from the left, which is the cylinder for the compressive testing, we can see that for normal strength concrete, there is a big spalling. All the area is being crushed, and all the chunks are being distributed over the area there. However, when we look at the UHPC specimen, we can see that the fibers are doing a very good job trying to limit the cracked area and trying to limit the spalling area as being shown in here. So here we are comparing between the modes of failure, between the normal strength concrete and the UHPC. For normal strength concrete, it's a brittle failure, flexural, purely flexural crack being in the middle. When we talk about the UHPC, we started having some cracks in the UHPC and the UHPC thickness. And then I didn't see any problems with the interfacial transition zone. I didn't see any issues with it. I didn't see any debonding. So it looks like we did a very good job when we were trying to prepare the specimens by providing 10 millimeter randomly with that tool we got in the lab. And then the crack also went up to the normal strength concrete substrate, leaving a wider gap in there. So if we compare between the different load versus displacement curves, we can see that for the normal strength concrete, maybe up to 20, maybe let's say about 35 MPa, 35 kilonewton, sorry, and at 0.5 millimeter, we have a brittle failure. However, when we talk about the UHPC, we can go up to barely 150 kilonewton. And then we start seeing some strain or displacement hardening effect despite the size of fibers we have. But if we had, for example, hooked end fibers, we're going to have a better performance. Maybe we're going to have some displacement hardening as what's shown into our lectures. So for the UHPC, normal strength concrete UHPC, the load was around 80 kilonewton, and then for the second specimen, we had a better behavior by getting more displacement hardening as being shown in here. Let's talk about the limitations now. So first of all, I'm gonna talk about the presentation. I'm gonna talk about the limitations in form of questions. I'm gonna ask you guys and ask myself at the same time. So first of all, when we add these UHPC layers, we're gonna have a lot of issues. I've seen that in at least 9 studies of 15 talking about the brittle failure. When we add more than enough in terms of the layer thickness, in terms of the configuration of where you're gonna put exactly your jackets or your UHPC layers. The second thing is basically what configuration? Is it only top or bottom or sides or U jackets? What's the thickness? Is it 25, 50, 75? What fibers? And also at what percentage? Then, what's the optimum interface bond preparation technique? Every study you see, sandblasting is the best. Epoxy adhesive is the best. But can we provide a rational way on how to provide an optimum interface bond between the UHPC and the normal strength concrete? And then, how can we make the interfacial transition zone between them stronger? Maybe even thinking in a crazy manner without even putting any preparation. Because I'm thinking from a practical perspective on the industry side, this kind of chiseling and hammering is going to take a lot of time. And I know that people in the industry don't like that kind of issues. Then, how efficient is this method? Is it costly? Is it better to keep using steel plates? That's another story. And at the end, bringing my perspective, life cycle analysis. I didn't see any study talking about the life cycle analysis for UHPC in repair applications. So this can be a very good introduction for some research papers as well. Now we're going to conclude our work having a little knowledge about machine learning, deep learning, artificial neural networks, and generative adversarial neural networks. I think that there are a lot of opportunities for people in computer vision to apply deep learning to study the different failure modes using convolutional neural networks, for example, because it's being applied for a long time on normal strength concrete. But I see and I have seen that the failure modes of UHPC are very different from normal strength concrete. So let's think of a way on how we can characterize it in using machine learning and deep learning. The second thing is I see a lot of trial and error in mixing the concrete. we always have this kind of issues, like what's gonna be the appropriate constituent in silica fume, what's fly ash, and let's think also about the microscopic way. What's gonna be the C3S and C2S in the ordinary Portland cement, and what kind of cement we're gonna use. And then at the end, a recent trend now is to use the generative adversarial neural networks. So this kind, based on the performance you need in terms of durability, in terms of cost, in terms of life cycle analysis, carbon dioxide emissions, whatever parameters you want, we can provide you with the mixed design that can respond to all your questions. So I think that's the end. Thank you very much, guys, for listening to my presentation. I hope that I didn't exceed the time.